So this afternoon, our seminar speaker is Dr. Stefano Nerozzi. He is a research scientist working with Jack Holt here on a number of projects, and also has his own research funding for through MDAP. He got his bachelor's degree from the University of Bologna back in 2008. And also a master's in geology and land management, and then went to University of Texas at Austin for his PhD in geological sciences, where his advisor was Jack Holt. And so Stefano came to the U of A in, what year did you come?
2020. I visited before, but 2020.
A good time to start.
Fine time in January, so a couple of months.
And so we're glad you're here. We're glad to be hearing from you. And the topic today is orbital radar sounding on Mars and beyond.
Thank you so much. Can you hear me fine? Awesome. So today I'm going to take you a little bit on a journey from Mars. The rest of the solar system is going to be guided by radars. Before I do that, there's a few problems here. Where's the mouse? Here. I think I need to select this. Now it works. Yeah. I would like to acknowledge the teamwork, not just my own work that was funneled into this presentation and the science I'm going to show you. So every person you see pictured here contributed one way or another to what I'm about to show you. So I'm very grateful for their effort. So today, again, I'm going to take you on a journey starting from the Mars North Polar regions, looking at a variety of terrains, mostly high sea terrains with radar. And then we're going to move to the lower latitudes where there is no more ice, but other interesting materials such as lava flows, which can also be probed with radar sounding. And then I'm going to show you how we can use all the knowledge and science analytical techniques that we learned on Mars and other planetary bodies and apply it together with new technologies to explore the rest of the solar system with radars. So starting from the North Pole of Mars, we are going to focus on Planum Boreum, the North Polar Cap, which you can see here in its topographic expression. It has many interesting features. Among those, there are steep scarps that expose the units that make up this polar cap. So at the base of this stratigraphic column, we have the so-called Rupes unit, which is dark in albedo, a little bit mysterious in its composition and origin. We know it's very old and likely made of a mixture of lithic spines and ice. On top of it, we have the so-called Cav unit, which has possibly similar composition, but is aeolian in nature. We see beautiful aeolian cross strata across all exposures. And on top of everything, capping and burying most of these units, we find the so-called North Polar Layer deposits, which are nearly pure water ice with exceptional layering, which reminds of our own Earth ice sheets, and we can use to reconstruct past climate change on Mars, just like we do on Earth. We can see the stratigraphy of these units, not only in visible images, but also in radar profiles. Here is an example across the entirety of the polar cap acquired by SHORAD, and which also reveals the internal stratigraphy of the MPLD and also the characteristic diffuse return from dunes of the Cavi unit. I forgot to mention that the Cavi unit and the Rupes unit are together called the basal unit because it's at the base, a lot of fantasy there. And it's going to be a little bit of the focus of the talk today because when we put all these units in a time perspective, we realize that the MPLD, despite their incredible layering and their importance in reconstructing climate, they only date back so far, in particular, depending on who you ask, somewhere between 4 and 10 million years old, which is a good time span, but evolution of Mars in terms of geological properties span a much longer time, that is probably covered by the other two units, Cavi and Rupes. This record is likely not continuous, not integral, but it's fragmentary due to erosion and lack of deposition. But it may be our only chance to reveal geological processes happening at the North Pole, dating back potentially to 3 billion years. So there are a series of motivating questions, in particular, how are all these geologic units related to each other? We know a little bit of it, but mostly they are buried underneath ice, so we want to reveal that with radar. And also, what is the extent and volume and the lithic versus ice content of the basal units? And also, what do they reveal in terms of surface processes and climates through their stratigraphy, composition, and also morphology? So, as I mentioned already, we're going to use the shallow radar, SHARAD, which is a 15 to 25 megahertz chirped radar, which gives it a vertical resolution of about 8 to 10 meters in water ice, so fairly high. And more importantly, it has basically complete coverage of the North Polar Cap. Here you see a coverage map where each ground track of an observation acquired by the radar is color-coded with topography, and you can see it's complete. There are only a few tiny gaps at lower latitude, meaning that the coverage is extremely dense. In fact, it's better on Mars than on Earth. And again, it can reveal the stratigraphy, not only of the MPLD, but also especially the Cavi unit, pretty much anywhere across planetarium. So the mapping, the type of mapping that we do is based on so-called the radar facies, which are essentially a comprehensive ensemble of characteristics of the reflection that the units give off to radar echoes. And in particular, the Cavi unit has a distinct diffuse return that was recognized by Brother et al. That can be distinguished from the sharp return of the Rupes unit. In some cases, we see through the diffuse return to reveal internal stratigraphy of Cavi, but we don't see through Rupes, which is until recently was kind of a mystery. In our mapping, we also include a mixed type of return, which shares a little bit of both types of units, so a little bit sharp, but also a little bit diffuse. And this is not the first attempt at measuring and establishing the extent of the basal unit. It was first done based on mock images by Fishbau and Ed in 2005, and later on with SHARAD, Putzig and others, and then Brothers and others complemented that with radar returns. However, at the time, there was not as much data, and the analytical and processing techniques were not as advanced. So we wanted to refine that and also address a potential inconsistency between these maps, because you may see that the extent of the basal unit is a little bit different in each map. So we wanted to understand that a little bit better. So here is a map of the radar facies, smooth here, essentially cover most of the top of the basal unit across and underneath Planum Boreum. Whereas the sharp return characteristic of Rupes outcrops, well, in radar, only in these regions right here. And we revealed the extent to be pretty much nearly identical to that of Fishbau and Ed, except here because it's completely buried by the MPLD, so there are no visible outcrops. And so that's revealing that they actually, even with limited outcrops, they did an exceptional job on mapping the extent. And really the difference between previous maps, the potential ambiguity there, was due to the fact that Brothers et al. Really mapped morphology, more like the actual extent of the unit. So we were really looking at a different kind of maps, and we just refined on them, essentially. Not only that, but we can also reconstruct the morphology of the basal unit underneath the ice. So here is a map of its morphology, and we identified that the reentrants that were erosional in origin and previously identified by Brothers are much more complex in their morphology, with like side reentrants and stir-step morphologies. And we also find extensive evidence of scarps that mostly face the equator all across Planum Boreum. These scarps appear to be erosional in origin, and in fact, in some cases, they correspond to spiral troughs that essentially dig through the MPLD. It's not really erosional, it's like a mix of deposition and erosion. And in some cases, inside into the cavity unit or rupus unit. But in other cases, the scarps are completely buried. And so we think that they are evidence of past erosion, perhaps a past more limited extent of the overlying MPLD, essentially excavating through the basal unit materials. We see a lot of other morphologies, but it would be a little bit too long to explain all of them. But in general, we find ample evidence of erosion through both the rupus and cavity unit. Not only that, but we also performed geologic mapping with the aid of one of my previous undergraduate research assistant, Maya Ortiz. And this was enabled by all the high wishes that the HiRise team granted to us. So I'm extremely grateful for that because it enabled essentially mapping of these units all across the all the exposures that there are around Planum Boreum, and in particular enabled us to define along with Sherrod what type of contacts we have between these units and also with the overlying MPLD and refine on where each unit was outcropping. Just with radar alone, it would have been particularly difficult to establish this, so it was really possible through integrated analysis of both type of data sets. So a little bit of a summary for this section. Sherrod revealed that the basal unit is more extensive than previously thought, at least compared to the work of Brothers et al. In 2015. And it also reveals previously unseen morphologies that tell us that there was extensive erosion across both units, rupus and cavity, which tell us in turn about something about their old previous erosional history. All of this work is actually contained and described in a paper that was published a few years ago. And however, there are a set of open questions that remain, and especially what is the exact composition of the rupus unit? Because as I mentioned, Sherrod is not able to penetrate through it. So we were able to establish the composition of the cavity unit in a separate work, but not with rupus. That remains still a mystery. And also, we know that there is extensive erosion of rupus, potentially feeding material for the growth of the cavity unit. But we don't know when it happened or what is the actual volume, because Sherrod can see a little bit of a contact between the two units, but not everywhere. So we are set to study the rupus unit in a little bit more detail. Here are some of the known characteristics. Is generally the outcrops are very dusty, and so that makes stratigraphic analysis based on visual imagery particularly difficult. Wherever we have good outcrops, we see that there is pervasive layering that sometimes extends for hundreds of kilometers, suggesting that the depositional process that created this unit was probably extensive in origin, like extensive in nature, probably a regional level. Some of these layers protrude more than others, suggesting potential changes in composition, at least moving vertically. And again, it's extremely difficult to penetrate with radar, impossible for Sherrod. Somewhere in some places possible with the other radar that I'm going to show you in a second. In terms of composition, we know that the rupus unit from spectroscopy contains a lot of ice and also some particular lithic materials, especially basalt alteration products, especially in the form of calcium and magnesium sulfates, in some cases hydrate too. And in fact, its erosion feeds a significant detection of gypsum across the dune fields in Olympia on the right here, probably fed by rupus unit right here. So we know that these materials are present, but we don't really know how much of them there are. So to understand that, we use the other radar that is currently orbiting Mars, which is called MARSIS. It operates at much lower frequency, which enables much deeper penetration at the expense of vertical resolution, about 10 times less than Sherrod. Nevertheless, it allows us to establish the internal stratigraphy of rupus unit and also cavity. And this was particularly enabled by a new set of data that was processed by JPL that corrects for ionospheric delays, but more importantly, distortions that are caused by the ionosphere and the usage of low frequencies. Just like Charade, there is complete enormous coverage of Planum boreum, so mapping across the entire region is very easy to do. And in particular, here I'm going to show you a preliminary results based on analysis at 3 different frequencies, 3, 4, and 5 megahertz, in an attempt to establish not only composition, but possibly frequency-dependent behavior of the components that may make up Rupes unit. And that is because what we are really measuring with radar is the so-called dielectric permittivity, which is a complex number. The real part is commonly called the dielectric constant, although that is kind of a little bit of a misnomer because it's not really constant. And it can be easily calculated if you know the two-way time delay from the surface to the base of a certain unit, which is very easy to determine with radar data, and by knowing the thickness of the unit, which we have from previous studies that we conducted over the basal unit. So the other part, the imaginary part, is associated with loss of amplitude of power in the radio waves as they go across a certain medium, in this case, the Rupes unit. So the math looks a bit nasty, but actually is relatively simple. And in particular, the only thing we need to determine, aside from the two-way time delay, is the amount of loss measured by the radar from the top to the base of the unit, which is relatively easy to do. Just measure the signal intensity. And we have a couple of methods to establish the so-called loss tangent, which contains in itself the imaginary part. And that is because most geologic materials, including all the materials that have been detected in Rupes, ranging from water ice to gypsum to basalt and weather basalt products, have known dielectric permittivities, both real and imaginary components. So if we can measure it for Rupes, we should be able to establish what kind of materials are present in there, in which percentages. And we do that by employing mixing power laws, in this case, a power law that was found in previous studies to be particularly effective for ice and lithic mixtures. And for those of you familiar with geochemistry analysis, you recognize ternary diagrams. We use exactly the same type of diagram to mix 3 different components and map the expected real and imaginary permittivities, and essentially establish how much of each material, in this case, water ice, gypsum, and weather basalt, may make up the Rupes unit. So the only thing left to do is to do the actual measurements. And here are the preliminary results at 3, 4, and 5 megahertz again. The results across all frequencies is that the real part of the permittivity is relatively low at about 4. You'll see there's quite a bit of spread in these distributions, and that is due to the fact that there is a significant spatial variability across the Rupes unit, and in particular, we found very high permittivities in this region, which is Hyperboreal Ingula. And in fact, you'll see that there are only a handful of samples here, and that is because even Mars has trouble penetrating through it and revealing its internal stratigraphy. And that is a symptom that there is a lot of loss in that particular region. In fact, when we look at the loss tangent, it is particularly high, much higher than what we expected. We didn't expect values this high, which are not typical of ice and are indicative that the unit must have either a lot of lithics or less lithics, but very lossy from the radar perspective. This amount of loss explains why Charade can't see through the unit. It's just that the higher frequency employed by Charade are not able to penetrate effectively through these materials. What we can do is to combine the 2 results using the ternary diagrams. So in this case, I'm mixing basalt, gypsum, and water ice for both the real permittivity and the loss tangent. And what we find is that there is only a tiny little overlap, suggesting that probably this mixture is not correct. There's something wrong with this. Much better overlap if we use, instead of basalt, weather basalt, which has much higher loss. And so it gives us this very nice overlap. And in particular, we find that the Rupes unit is likely made of almost 90% ice. And the rest, the 10-15%, possibly made either of a mixture of hydrated sulfates, such as gypsum or magnesium sulfate, and other weather basalt products. This is not, I mean, in terms of composition, this is not entirely surprising because some previous studies suggested that there may be significant amount of ice, but we were not expecting this much ice. Now, the question becomes, where do these materials come from, especially the weather products? And it has been suggested in the past that either you may have transport of these altered materials from elsewhere on Mars. After all, this unit seems to be accumulated from a widespread process, perhaps falling dust, retaining water too. Or it could be just that the dust was actually basalt that then was altered through essentially the 3 billion year history of the unit in situ, even at very low temperature. And this has been suggested before for the case of gypsum in particular, about 12 years ago. So not only that, but we also mapped the contact between Rupes and Cavi because Marsis can reveal it pretty much everywhere across Planum boreum. Same technique that we used previously with Chorad, but in this case applied to Marsis. And we combined the data that also we previously acquired from 2D mapping with Chorad and also a newer 3D volume that was constructed based on the very dense coverage by Chorad. And in this case, this is the work by Rocio, one of our students who is currently mapping this content in this 3D volume. And by combining all these data, we constructed what I think is the first ever extent and thickness map of the Rupes unit, revealing that, well, as previously thought, it is confined to the Western hemisphere of Planum boreum. It is particularly thick, and the volume, a little bit unexpectedly, is actually the slight majority of the total basal unit volume. And if you add into it that there are some lithics into it, you'll realize that there are a lot of sediments that have been trapped in this unit since potentially 3 billion years ago when this unit was accumulating, which is in terms of global equivalent layer, a layer of 26 centimeters. So imagine 26 centimeters of materials actually not accounting porosity, so actually thicker everywhere on Mars, then removed from somewhere and locked here for potentially billions of years. So probably something that goes into the general transport, not only of ice, because there is a lot of ice, but also sediment that have been trapped since then here. So a little bit of a summary. Not just Chorad, but also Marsis can reveal important properties of the basal unit, in particular Rupes. And it allowed us to reveal that there is not only a lot of ice, but a lot of likely basalt alteration products, which make up a significant amount of materials, of sediments that have been locked into this unit. And also that, by combining data from different radars, we can really reveal the internal stratigraphy of these units and in turn, the potential climate record dating back billions of years. This is not the end for the North Pole of Mars because we have students such as Maya Willis-Reddick currently working on some mysterious Chorad reflectors that I identified many years ago, and she has extended the mapping of these reflectors outside of Planum boreum, and she associated this mapping with geomorphic mapping to establish what these materials may be made of. She applied the same loss tangent inversion techniques that I showed you earlier with Marsis, in this case, Chorad, and essentially found that the loss tangent is particularly low. So we think that these materials are very rich in water ice. After all, we are at about 80 degrees north, and the Phoenix lander at 70 degrees north, essentially, it would be out here in the map, found that there's nearly pure water ice underneath just a few centimeters of sediment. So it's not really unrealistic to think that there is a lot of ice even outside the polar cap, just buried under other sediments. Next, I want to show you how radars can reveal properties and stratigraphy of other types of units that don't have any ice, which are typically more difficult to image, but it's still possible. So in this case, we are in southeastern Utopia Planitia, here on Mars, next to the Elysium Mons volcanic complex, near the outflow channels of Ebrus Valles and the Festus Fosse, which are well-preserved outflow channels carved by potentially catastrophic floods, dating back potentially billions of years. In fact, the units that they in size are about 3 billion years old. There is also widespread evidence of either mud volcanism and or lava ice interactions in the form of pit cones. Just a couple of weeks ago, Mackenzie Mills was defending her dissertation and showing how this region is pervasive pitted cones that have these mysterious origins. So I highly recommend to check out her work. And for all these reasons, it has also been proposed as a human landing site because it's particularly easy from the engineering point of view to land here. So in terms of radar, there is one main guiding question, which is what is the subsurface structure and composition of the geologic units in this region? So we apply the same techniques that we applied before at the pole, but in this case at lower latitudes, and identify that there are several clusters of subsurface radar reflectors occurring here in the north in Granicus Valles and Ibeleus Fosse. A small cluster actually right next to the channels, which is a little bit interesting because nothing else occurs near them. And also a large cluster here, down here in Ibeleus Dorsa. And to examine the possible composition, we applied exactly the same techniques that we employed at the North Pole, so for lost tangent. And in particular, in the north, in Granicus Valles, we found that these clusters are associated with the different thermophysical units that have been previously recognized to be associated with lava flows and lavas from the Elysium volcanic complex. After all, there are lavas everywhere here. And in fact, the composition in terms of lost tangent suggests us that these materials are essentially basaltic lava flows, compatible with the findings of a similar study just to the northwest of here, which also find fairly high lost tangents compatible with basaltic lava flows. So kind of confirming this volcanic origin hypothesis for these materials. Near Ebrus Valles, I mentioned that there is this small cluster of reflectors just next to these beautiful erosional channels. In this case, the lost tangent is a little bit lower, kind of intermediate values, which are can be either explained by low loss lava flows. They have been measured before on Mars, especially by Emily Shoemaker, one of LPL alumni, but it is also compatible with other sediments mixed with lava flows that have been identified in Amazonas Planitia. So in this case, given the widespread volcanism that we find in this region, we think that is potentially kind of a mix of the two. And in particular, the localized occurrence of these reflectors, we think is associated with a particular alternating stratigraphy that can be detected by SHORAD here, but cannot be detected elsewhere because you just don't have the right contrast in dielectric permittivity. Last, Ibeleus Dorsa, very different story from the two other regions because we find very low loss tangents. In fact, reminiscent of water ice because they are particularly low. However, thermal modeling of ice stability suggests that ice should not be stable in the subsurface at these low latitudes within the first few 300 meters from the surface. So instead, we think that we are possibly dealing with either very high porosity sediments or perhaps hashfall deposits, as, for example, previously suggested for the so-called Medusa fossil formation, because it occurs not very far from here. It kind of straddles the dichotomy between highland and lowland terrains on Mars. And this is not very far from the westernmost occurrence of this unit. And it has been previously proposed that this unit is it's essentially alternating hashfall deposits, possibly originating from Apollinaris Mons right here. And its distribution is essentially due to ashfall dispersal patterns as modeled by global circulation models. And in fact, we are in a region here in the outskirts of this ashfall deposit pattern. So it is plausible that we are looking at ashfall deposits that then have been capped with lava flows. So to summarize what we found here, subsurface radar sounding not only reveals subsurface structure, but informs us that in this region, there is widespread volcanism, ranging from lava flows to mixed sediments and lavas, all the way to potential pyroclastic deposits belonging to the westernmost occurrence to date of the Medusa fossil formation. So hopefully this kind of suggests you that radar can really be used across a wide variety of terrains, not just ice that is relatively easy to probe with radar. And from this, having gained all this knowledge, I want to take you to our more recent efforts in developing what we consider to be the next generation of radar sounders. So radar sounding is actually not a new thing. In fact, it started with the human exploration of the moon, in particular with the Apollo Lunar Sounder Experiment, or ALSI. At the time, it was a set of antennas mounted on the service module of Apollo, and an astronaut had to get out to do an EVA to retrieve a cassette with films to retrieve the radargrams. Now we don't have to do that anymore. But this instrument was really the key to confirm the hypothesis that, for example, lunar maria are nothing but extensive, thick basaltic lava flow deposits. You have seen Marsis and Shorad. I wanted to highlight the fact that there is a little bit of a compromise between penetration depth and resolution. Marsis operates at low frequency, so it can see very deep, but at low resolution. Conversely, Shorad sees only at shallower depths, but much higher vertical resolution. So that really plays in the design of a radar. And in fact, Reason and Rime, which have recently launched, in fact, Europa Clipper with Reason launched like a week ago, employ, among other frequencies, intermediate frequency around 9 megahertz that kind of take advantage of both deep penetration and somewhat high resolution, especially Rime with 3 megahertz bandwidth. Both employ dipoles. In the case of Reason, actually an array of dipoles to perform, array combination of the radiation pattern of the antennas, and we'll see in a second why they chose to do that. But again, just like Marsis and Shorad, they all employ fairly large antennas. Slightly different story for CONSERT. In this case, it was a so-called bistatic radar because the transmitter and receiver were in 2 different places. And in particular, the transmitter was on the Philae lander, which had a very rough approach to the comet, but it landed and it worked, in fact, a couple of times. And the Rosetta main spacecraft received signals along the 2 paths highlighted here in red and blue, and allowed us to determine what is the subsurface structure and composition of the comet, essentially confirming that it is icy material with decreasing porosity as you go deeper. It operated at much higher frequency also because the antennas couldn't be too large, so they had to fit in the small Philae lander. However, in general, radar sounders, especially if you go low in frequency, require large antenna systems, and their size and weight is is essentially confines them to large flagship missions. They are nearly all flagship missions. They also all have a single linear polarization, which is good to do a wide variety of studies. I just showed you a bunch. But for example, linear polarization is affected by ionospheric Faraday rotation, which is a phenomenon where your polarization gets rotated in the presence of ions and a magnetic field. And so that tends to lead to attenuation of radio waves, so less signal coming back to the radar. And also complex polarization is kind of the key to understand particular properties of the surface and subsurface materials and structure. Also, most of these antennas, with the only exception of Reason, which employs an array again, are not capable of direction of arrival. And that is important because in this example of a radiogram across the North Pole of Mars taken by Sharad, we see beautiful layering, but we also see a lot of other signals that are actually the so-called clutter. Clutter is nothing but echoes that don't come from nadir, from right underneath the spacecraft, but from the sides. And that is due to reflections from the topography that exists on virtually any planetary surface, right? So Reason uses an array of antennas to essentially collimate the radiation pattern into a narrower beam and essentially reject clutter. But otherwise, all other radars are not capable of this mitigation. So the only thing you can do is to simulate clutter and hope that your signals of interest are not overlapping with it, because it's basically impossible to separate the two once the data is acquired. So here, the game changer for all these issues is to employ a so-called vector sensor antenna. This is not a new concept, but it's advanced enough that it was somewhat challenging to implement until recently. And it's a set of antennas that can measure all three-dimensional components of both the electric and magnetic field of incoming radio waves. This allows you to compute the so-called Poynting vector, which essentially tells you where a signal comes from. So essentially, we can detect, for example, where clutter is coming from and essentially reject it and only keep, for example, the nadir return. We'll see more about that later. It's also inherently full polarizations. We can employ all polarizations, and we are not affected, for example, by Faraday rotation in a ionosphere. This antenna is going to be soon demonstrated in space around the Earth by the AeroVista mission developed by MIT to study auroral Earth emissions and also galactic and extragalactic radio emissions that occur between 0.1 and 15 megahertz. The whole set of antennas is actually stored in just a 2U volume, which is a volume of about this size. And the whole spacecraft, including the stowed antenna, fits in just the 6U. Here is an example of one of the prototypes. And here I have a 3D printed model, scaled down, of course, of the antenna system. You can look at it. It's a little bit fragile. Be careful not to stab in your eyes with this. But that's what the spacecraft with the antenna is going to look like. And it has been extensively tested at MIT in its deployment and also in its electrical and mechanical characteristics. But really, what I want to insist on a little bit, its ability to mitigating and reject clutter. So here is an example of a debris-covered glacier in the southern mid-latitudes of Mars. There are a couple of Sharad profiles, so you should be somewhat familiar with them now, where we see not only the surface, but a lot of what look like subsurface returns. However, when we compute the clutter simulations, we find that a lot of these signals are actually clutter. And mixed with them, there's actually some real signals. So the big advantage of the VSA is that we can only select a very narrow beam of only a few degrees, like about 3 degrees, that's the capability at Mars, and essentially reject all the clutter that is not depicted in green here. So essentially, we could reject all the clutter in the deeper subsurface. So making interpretations of actual subsurface reflectors very easy to do. So the only thing that is missing from the AeroVista system is a transmission system to make it a radar. So that's what we did recently at MIT, and we are currently developing here, thanks to the UA Space Institute funding, which we are very grateful to, because we were able not only to measure and confirm that the radar has the electrical characteristics that we modeled and simulated, but we were also able to test a whole transmit to receive path that would be employed in a real case scenario by transmitting a chirped pulse and processing it to obtain a compressed pulse, which is a little bit distorted because there were interactions with the chamber walls, but it worked. So we demonstrated an actual radar system at 2 different frequencies. This all funneled into 3 different proposal programs, one of which is WHISPER, the wideband HF heights and subsurface penetrating radar. I was PI on this, and it operates at the native operating frequencies of AeroVista, 10 to 15 megahertz. It can be used on virtually any planetary body on the solar system. I showed you how CONSORT was used on a comet, so we could use it there. Or we could use it on larger bodies, including moons, but even gas giants, oddly enough, because we will retain all the capabilities of AeroVista and, for example, measure auroral emissions in the gas giants. Or we could do active ionospheric sounding by employing active radio pulses, just like Mars does on Mars to study its ionosphere. The whole instrument, again, has been demonstrated to TRL 4, and the proposal was aimed to raise it to TRL 6. To also demonstrate these capabilities, we performed a set of clutter simulation at Ceres in Occator Crater, and particularly crossing Vinalia Facula, which has been suggested as a priority target. And without clutter rejection, it will be a nightmare to look for reflectors in the subsurface here. Similar story, a little bit better actually, fortunately at Europa in the Radamantes region, where we have all these linear ridges and fractures, which as clutter, they really resemble subhorizontal radar reflectors. So with a VSA, we could reject the vast majority of this clutter. Without it, good luck. I'm really glad that Europa Clipper has reason with beam steering capability. Based on the RIME reason and also Mars's mission profiles, I was able to model the expected performance in terms of signal to noise ratio of our proposed radar, and essentially we can get a better SNR at down to 400 meters depth, for example, at Mars compared to Mars's, and we can very closely match the performance of RIME and Reason, but with a much more compact, lightweight antenna system. Not only solar system in general, but also we focused on the moon with Acorn, similar radar, but working at higher frequencies, which actually make the system even more compact, because instead of being like about 4 by 4 meters across, it's only 2 by 2 meters, because we are working at smaller frequencies. And we could probe a wide variety of terrains on the moon, ranging from regolith to lunar maria, but we are especially interested in detecting and characterizing ice at the South Pole, where it is thought to potentially exist in permanently shadowed regions, which unfortunately are typically contained within craters. And just like Occator Crater on Ceres, the clutter is kind of a nightmare. But again, with the VSA, we are able to isolate actual subsurface returns and distinguish them from clutter. In this case, I didn't have a mission to base my SNR estimates on, So I had to learn and funnel my inner Kerbal Space Program knowledge into GMAT, the General Mission Analysis tool, which is a free tool. Highly recommend everyone to check it out from NASA. And essentially because I needed to know what are the expected tangential velocity and altitude profiles of a mission at the moon. And with that, I was able to do a similar SNR estimate that I did for other bodies, but in this case for the moon. And essentially we can probe through all kinds of regolith, including lossy regolith and also pretty much all types of ice, including lossy ice mixed with regolith, and a probe to 100 meter or more into lunar maria also, and exceed the SNR of the Lunar Radar Sounder, which is another radar on Kaguya, which orbited the moon, and essentially get good data on the moon as well. Last but not the least, the Earth. This is a third instrument proposal development program, and in this case aimed at mainly at probing the ice sheets on Earth. And that is because, ironically, we have better coverage of the ice sheets on Mars than on Earth. In fact, there are big gaps that for a long time now has been called on to fill in, because knowing the bed topography of ice sheets on Earth is the key to understand how ice flows and eventually contributes to sea level rise, especially fast flowing ice. So again, I use GMAT in this case to model mission profile around the Earth. And this is an example of coverage over the Lambert ice sheets here in Antarctica. And in just 6 months, we can get a very dense grid, and over a 2-year mission lifetime, which is a mission without any reboosting after launch, we can cover 100% of the Greenland ice sheet from top to bottom. The vast majority of fast-flowing ice, which is the major contributor to sea level rise in Antarctica, and about a third of the deeper Antarctic ice. But that is not really the limit. We can also probe arid regions, high latitude permafrost, or really any terrain on Earth. I mean, the options are nearly limitless. So I'm going to leave this summary about instrument development up here, and I'll take any questions. Thank you very much.
Thanks for the great talk and summary of all you're doing. I was wondering, if you believe SpaceX, there's going to be, big payloads and big masses before too long. Does that open up, like with longer baseline, longer wavelength things, like a really big 100-meter scale things you might deploy, and what could you do with that?
Absolutely. This focus on developing small sat instrument is due to the fact that these are our current capabilities, and probably for at least the next few years. Of course, if we could launch something bigger, for example, we could make that kind of antenna a little bit larger, not be confined in just 2 U's, and that could actually give us better electrical properties, especially at low frequencies, because I showed you how we can closely match the performance of rhyme and reason, but those radars having bigger antennas have necessarily better efficiencies compared to us. So, if we can get that kind of sizes, then we could do even more science, of course. And if we can go even lower in frequency, we could probe even deeper into certain materials. So, for example, on Europa, the high shell thickness is thought to be up to about 25, 30 kilometers. It will be very challenging for all these radars to penetrate that deep, unless the ice is particularly cold and low loss. With even lower wavelengths, we could most likely certainly detect that ice-ocean interface. On Ganymede is thought, I think, to be the high shell thickness about 100 kilometers. That would require a lot of power, which is only possible with large spacecraft, but also very large antennas that operate at very low frequencies. However, you need to keep in mind that in some places, ionosphere is an issue, and if you go too low, you're gonna be within the plasma frequency, and essentially all you're gonna see is the ionosphere. So you can do ionospheric sounding, but you're not going to see a subsurface. Of course, for icy moons, that shouldn't really be a problem. Maybe on Europa, there's a little bit of debate there on performance, but shouldn't be too big of an issue. But for example, at Mars or Venus or Earth, that would not be possible, which is why, for example, on Earth, we employ high frequencies.
Thank you. Any questions from the room or online?
No, John Hill says, thanks for a great talk. Thank you.
Alfred?
What do you think of the radar proposed for the International Mars Ice Mapper mission, even though it's not going anywhere? What do you think of that Canadian SAR?
Well, I was part of the measurement definition team for that one, and also the instrument definition team for the VHF sounder that will complement it. I actually hope, it's currently, it's not really going anywhere, but it's not dead. It's worst case scenario is kind of zombie state, but it can be resuscitated. Especially the other partners, non-NASA, are still very invested into it, especially Canadian Space Agency, which has been.
What do you think of the radar itself, though? How useful is it?
Well, I think it's going to be potentially a game changer for exploring the shallow subsurface of Mars. I mean, I showed you how you can achieve high resolutions with SHORAD compared to Mars's. In that case, it would be much higher resolution because you would not be operating, instead of 20 megahertz, you would be operating at 900, and with a much wider bandwidth, in fact, 16 times, which turns into 16 times better resolution. So you could resolve layer thicknesses of just a few tenths of centimeters in certain materials such as ice or overburden. So I think it's potentially a game changer. So I truly hope it's actually going to be revived, and it's we are going to be able to examine the data, especially for its interferometric capability, which we use extensively here on Earth, and will be the key for detecting, for example, subsurface ice, but any sort of material really on the rest of the surface of Mars.
Any other questions? If not, let's thank our speaker again.